Hello everyone, the topic of this presentation is towards accurate and efficient pixel-level video understanding. I'm Yunchao. For pixel-level video understanding, video object segmentation and video scene parsing are the two most related research areas. Video object segmentation is actually a semi-supervised segmentation task. In this task, given the user-provided object masks at the first frame, VOS approaches are required to predict the object masks in the subsequent video frames. In VOS, we can have one or more tagged objects. Video scene parsing is a semantic segmentation task for videos. It requires to recognize the semantics of each pixel in the given videos. We show several examples here. In these videos, different colors indicate different categories. For scene parsing, we not only need to recognize a scene object like a human, car, bus, we also need to recognize those semantics from stuff categories like ground, tree, sky. Beyond the common challenges existing in image segmentation tasks, pixel-level video understanding poses many new challenges. For example, motion blur will appear when an object is moving very fast. During the moving, this object may also be occluded by other objects. Besides, the appearance of this object may continually change during the movie. These challenges further increase the difficulty of pixel-level understanding in videos. In this talk, we will introduce our latest progresses on how to perform accurate and efficient video object segmentation and video scene parsing. I will introduce the first two works, and my students Zongxin and Jiaxu will help introduce the following ones. These works achieve state-of-the-art performance on some popular benchmarks. So the first is collaborative video object segmentation by foreground and background integration. This work was published in ECCV 2020. This is the most related work to us, which is from Google. This work purposes to perform explicit matching with pixel-wise embedding for VOS. Particularly, given the feature embedding of the current frame at T, VOS performs the global matching between the pixel embedding of the current frame and the reference frame, where the GT ground truth masks are provided. And additionally, it performs the local matching between the pixel embedding of the current frame and the previous frame, where the masks are predicted at the previous step. Then the two matching score maps and the previous predicted masks are concatenated together with the feature embedding to make the final prediction. To better understand the matching effect, here we show the visualization maps of global and local matching maps. Our work is motivated from this failure case. Current works pay little attention to the feature embedding of background region in videos and only focus on exploiting robust matching strategies for the foreground object. As shown in this picture, if we focus on only the foreground matching like field VOS, a similar and the same kind of object in the background is easy to confuse the prediction of the foreground object. Such an observation motivates us that the background should be equally treated compared with the foreground, so that better feature embedding can be learned to relieve the background confusion and promote the accuracy of VOS. Based on the above motivation, we propose a novel framework called CVPR. In CVPR, we not only extract the embedding and do match for the foreground target in the reference frame, but also for the background region and to relieve the background confusion. This is an overview of the CFBI. The red and blue colors indicate foreground and background respectively. Next, I will introduce some important modules within CFBI. In FieldView-S, the local matching is limited in only one neighboring window with fixed size. However, the offset of objects across two neighboring frames in ViewS is variable due to different learning rates. So we propose to apply local matching on different skills and let the network learn how to select a suitable local skill, which makes our work more robust to various moving rates of objects. We should note that we use intermediate results of the local matching with the largest window to calculate on other windows, so the multi-skill local matching accurately does not increase too much computational cost. In addition, we observe that the pixel level matching is not sufficient and robust to matching those objects with larger scales and may bring unexpected noises due to the pixel-wise diversity. So we introduce an instance level embedding to help the segmentation of large-scale objects by performing attention operation. We first use the average pooling to extract the instance level foreground and background embedding of the reference and the previous frame. And the embedding is then expanded to a 2D feature maps and input to the collaborative ensemble to help make the final prediction. Here is the comparisons of our method with the other state-of-the-art method on three popular benchmarks. We can see that our work can achieve the best performance on all three benchmarks. This is an improved version of CFBI. We called it as CFBI Plus. The main difference lies in we perform feature matching across feature maps of different skills. To reduce the computational cost, we utilize ultras matching. As shown in this figure, we adapt larger dilated rates to choose the pixels for matching on the larger feature maps. In this way, we can significantly improve the accuracy without introducing too much computational cost. And the result shows that we achieve a much better performance on the YouTube ViewS benchmark. Here we show some visualizations of the effect of our CFBI method. We can see that even for the very challenging cases, our CFBI can still produce satisfactory results. We further examine the effectiveness of our CFBI series using different backbones such as MobileNet and RaceNext. The code and all trained models are available on GitHub. In the next, Zhongxin will help introduce our latest progress in ViewS using Transformer.
Thank you, Yunchao. I'm glad to introduce our latest work associating objects with transformers for video object segmentation here. Our latest work is currently under review, but we have achieved the first place in the third UG2 large-scale video object segmentation challenge, which is also a workshop in CVPR2021. At the beginning, I want to revisit previous VOS solutions. Modern video scenarios commonly contains multiple targets. Under these cases, previous VOS methods prefer to decode each object individually, and ensemble all the single objects result into a multi-object prediction. We call this manner a post-ensemble manner. This post-ensemble manner is easy to focus on each foreground object and ignores the possible similar objects in the relative background, leading to a background confusion problem. As shown in this figure, the similar background shape is matched with the blue target incorrectly. To relieve the background confusion problem, our previous solutions, CFBI and CIBI Plus, proposed to integrate both foreground and background information by additionally matching the relative background. We mark the background matching in dotted line here. The foreground-background integration can explicitly augment the learning of foreground-background contextual information, thus effectively relieves the false matching in background. However, CFBI still uses a post-ensemble manner. Such a manner makes the design of network architectures easy, since the networks are not required to adapt to different target numbers and only responsible for a single object. However, processing each target individually will consume multiple times single object computation under multi-object scenarios. Besides, the contextual information among all the objects cannot be learned at once uniformly and efficiently. To avoid using the post-ensemble manner, and thus learn contextual information more effective, inform multiple targets more efficient, a better solution should be able to associate all the objects at once. Thus, we carefully design a novel framework, AOT, to embed, match, propagate, and decode all the objects uniformly for VOS. Next, I will introduce our latest VOS framework, AOT, associating objects with transformers. This figure is an overview of AOT. As common, the predictions are generated in a recurrent manner. Two important key parts are proposed here: identification mechanism and the non-shortened transformer. The most important part of AOT is our identification mechanism. We use this mechanism to associate multiple objects as simply and efficiently as processing a single object. In detail, the identification mechanism has two components: identification embedding in the left and the identification decoding in the right. For multi-object scenario, we first transfer the multi-object mask into an identification embedding by assigning identities to each object. Obviously, the identification embedding contains the mask information of all the targets. We build a large identity bank to store all the identities. Each identity is a vector. For associating and decoding all the objects, instead of propagating single object masks like previous VOS methods, we propagate our multi-object identification embedding from memory frames to the current frame at once. Thus, we can learn the correlations among all the objects and decode their probabilities and segmentations uniformly. Since we have defined all the identities, we will first decode the probabilities for all the identities during the decoding. After selecting the identities assigned before, we can easily get a multi-object prediction. Such a pipeline is a simple yet effective approach to avoid using the post-ensemble manner. Previous works always use a single matching layer or multiple matching layers but in parallel for VOS. For example, our CVPI and CVPI Plus do multiple matching processes with foreground or background or different scales, but these matching processes are individual to each other. In our ALT, we found an individual process of matching and propagation is not enough to sufficiently model multi-object correlation or association. Thus, we carefully design a long-shorten transformer structure for building hierarchical matching and propagation. The LSKK block is based on the well-known transformer block, and we further introduce long-term attention and short-term attention for conducting VOS matching and propagation. The long-term attention performs a long local matching from long-term memory frames. In contrast, the short-term attention conducts a local matching from a small spatial temporal neighborhood for each position. The hierarchical LSTT is not a simple combination of multiple attention layers. We visualize the long-short-term attention maps in different LSKK layers, from shallow layer L equal to 1 to deep layer L equal to 3, as shown. In the shallow layer, the long-term attention map is very coarse, but in the deeper layer, the attention map becomes very accurate. In other words, hierarchical matching and propagation obtains better accuracy in deeper layer since the shallow propagations will have the deeper ones. Besides, since the right person is occluded in the previous frame, the shortened attention fails to match her, but we still predict the right person correctly because of the accurate long-term attention in deep layers. To compare ALT with SOTA methods, we build a series of ALT variants with different LSKK number and different complexity. We follow the common training strategy with list augmentations. Even using lightweight encoder and decoder, MobileNet V2 and FPN, our ALT large significantly outperforms previous SOTA methods on the largest VOS benchmark, UG2 VOS, while maintaining a better multi-object speed. Besides, our smallest ALT Tiny can maintain a real-time speed. Thanks to the hierarchical structure, we can simply adjust the DLSKK number to balance our ALT between SOTA performance and the real-time multi-object speed. Next, we want to show some results of our ALT large without using any test time augmentations. Our ALT is robust to many challenging cases in UG2 VOS, such as similar objects, occlusion, fast motion, and other mixed cases. We hope our ALT will serve as a solid baseline of VOS. Particularly, we hope our identification mechanism will ease the future study of multi-object VOS and other related areas.
Thanks, Zongxin.
Thank you.
In the next, Jiaxu will help introduce our recent work on video scene parsing. In this work, we propose a large-scale benchmark to facilitate the video scene parsing in the wild.
Hello everyone, I'm Jiaxu Miao. Now I'm very glad to introduce a large-scale dataset for video scene parsing, VSPW. So first, why we propose a large-scale dataset for video scene parsing? As we all know, scene parsing is one of the main problems in computer vision. Recently, image-based scene parsing methods have been well explored. However, the real-world applications, for example, autonomous cars, usually use video data. So, learning to perform video scene parsing is more reasonable and practical. Previous datasets for video scene parsing have some limitations. For example, cityscapes and NYUV2 only annotate one frame or some non-adjacent frames in a video clip. So actually, these datasets are image-based. CamVid has temporal annotations. However, the scale of CamVid is very small. It only has 6 videos, 701 annotated frames. Besides, the variety of these datasets is very limited. For example, cityscapes and CamVid only focus on one scenario, the street view scenario, and NYUV2 only focus on indoor scenarios. So, to advance the video scene parsing task, we present a large-scale video scene parsing dataset, VSPW. This figure shows the scale comparison between VSPW and previous datasets. VSPW has more than 3,000 videos, more than 251,000 annotated frames, which is about 100 times larger than previous datasets. The variety of VSPW is very large. The videos of VSPW are from more than 200 indoor and outdoor scenarios. For example, the riding farm, the kitchen, the street view, and so on. For comparison, cityscapes and CamVid only focus on the street view scenarios, and NYUV2 only focus on indoor scenarios. These two videos show the annotation frame rate of VSPW and CamVid, and VSPW has much larger annotation frame rate than CamVid. In a word, VSPW is a large-scale dataset, and it has well-trimmed long temporal clips, and the temporal annotation is dense. The pixel-level annotations are provided at 15 frames per second, and the videos from VSPW has high resolution. The large-scale dataset VSPW brings some new challenges. For example, how to improve accuracy and efficiency of segmentations by exploring temporal information. And different from image-based datasets, for VSPW, we need to improve temporal stability of predictions. And different from images, videos have motion blur, object appearance change, and occurrence. Besides, VSPW has some very similar categories. For example, dogs and cats, horses and cattle. So we need to design fine-grained models to tackle the problem. And VSPW is a long-tail dataset. So how to improve the performance of the tail classes is very important. Besides, we can use VSPW for some new applications. For example, we can use VSPW to pre-train models for semantic segmentation. We can study domain adaptation or transfer learning or tracking using VSPW. Collecting such a large-scale dataset for video sympathizing is not easy, so we use a human-computer collaboration strategy. Step 1, some expert annotators provide video category annotations. Step 2, common annotators provide pixel-level annotations at 1 frame per second. And next, we use VOS models to propagate the annotated label from 1 frame per second to 15 frames per second. The generated masks by a computer are not good enough. So some common annotators refine the masks, and the refined mask can be used as the input of the VOS model. MILU is usually used to evaluate the segmentation performance. However, different from image sympathizing, for video sympathizing, we need to evaluate the temporal stability of predictions. Previous methods have proposed the temporal consistency score, the TC score, for evaluating temporal stability. Here we propose a VC score to evaluate the temporal stability. The left figure shows the TC score, and the TC score only uses 2 adjacent frames to evaluate the temporal stability. However, our VC score can evaluate temporal stability in a long temporal clip. We evaluate some image-based and video-based sympathizing methods on VSPW, for example, PSPNet, ARPANET, NetWarp, and so on. Besides, we propose a simple temporal context blending network to leverage context information from temporal domain. It is based on PSPNet or OCRNet. First, we use PSP or OCR to extract context information at 1 frame, and we blend the temporal information on the temporal domain. The results show that TCB can slightly improve MILU and significantly improve the temporal stability.
Okay, in this talk, we introduce our latest progresses on video object segmentation and video sympathizing. For video object segmentation, we introduced the CVPR and its improved version CVPR Plus. We also introduced our recent work, which is the first one applying transformer to facilitate the video object segmentation. For video sympathizing, we introduced new large-scale benchmarks to facilitate the research. And in this work, we also present a new VC metric to evaluate the smooth of the predictions. Also, a TCB network, which can be trained in an end-to-end manner, also introduced. In my opinion, pixel level understanding is very important research topic in the future, which still have a long way to go. We will hold the first video sympathizing the world challenge in the ICCV workshop, and welcome to participate. Okay, thank you.